And so now we're going to look at the interior angles. Now, when you think about a polygon, guys, you've got the inside of a polygon and you've got the outside or the exterior of the polygon. And we're going to talk about the interior right now. And the interior angles, remember what Mr. Scritchfield said at the beginning, that a polygon has many angles. And so we're going to look at those many angles from the inside of the shape. And so when you think about that, okay, you get this idea of interior angles. Now, the sum of the interior angles of any convex polygon can be found using. So what it's saying here is we can find all of the degrees altogether of all the interior angles by using this formula here that says that the sum of all the interior angles equals the number of sides minus 2 times 180. Okay, and n means the number of sides. Okay, and this is one of those things where you got to commit this to memory, that n means the number of sides. Okay, how many sides does the shape have? Okay, so you take that, minus it from 2 and times by 180. I mean, it's pretty straightforward here. If you're looking at an octagon, that's 8 sides, so you just go 8 minus 2, which is 6, times it by 180, and you get, what is that, 9... No, I'm way off. 1,680 or 1080. 1080. So I can't do the math in my head, but you have a calculator to help you out with that. Yep. So anyways, I mean, it's pretty simple stuff here, guys. So here we have a pentagon, okay? And so to find the amount of degrees of those total angles on the inside of the pentagon, we're going to add up the number of sides, and a pentagon has 5. Okay, so then we just substitute in the formula. Instead of n, we pop a 5 in there. 5 minus 2 is 3. 3 times 180 is 540 degrees. I mean, it doesn't get any easier than this.
Yeah, it doesn't have to be a regular pentagon, just any pentagon, any 5-sided convex pentagon. All the angles always add up to 540 degrees, no matter what.
And it's kind of like triangles, guys. Triangles always have to add up to 180 degrees.
Right.
Okay, a regular convex, or any convex pentagon is going to add up to 540 degrees. It's just kind of, it's bound by that
In fact, that's where it comes from.
Yeah.
It comes from, if you were to draw lines from one vertice here, so from one vertex, if you drew a line like straight across that pentagon, you'd create a triangle on top. If you created a diagonal to the bottom right vertex, you'd create another triangle and a third triangle. So the n minus 2 is what tells you how many triangles end up being inside that shape.
Sounds like a pretty good in-class activity.
Yeah, it would be. And so because there's 5 sides, you can draw 2 diagonals that separates the pentagon into 3 triangles. So the 3 triangles all have 180 degrees in them. So 3 times 180 is what all the angles inside of a pentagon add up to. Works that way for any shape.
Yep. I mean, I think the toughest thing is remembering the formula.
Right.
That's pretty much it.
Yep.
And that's why I have notes.
Yep. Just subtract 2 from how many sides there are, multiply by 180 because that's how many triangles it is.
Here we go.
Okay.
All right.
So if we look at another example, just same thing, just going backwards though. This one says if the sum of the measures of the interior angles adds up to 900 degrees, what type of polygon is it? And so we're just going to take the formula that Mr. Bedella was just using in the last slide and set it equal to 900. So we're going to take the n minus 2 times 180 because we don't know how many sides it is. So we can't plug in for n. That's what we're trying to figure out. How many sides does it have? What kind of polygon is it? So n minus 2 times 180, we're going to set that equal to 900 because that's what they told us they add up to. So to solve this equation, yes, you could distribute the 180 and make it 180n minus 360 and then solve from there. That would just take too long. So just divide both sides by 180 to get rid of the 180 on that side. So if we divide both sides by 180, well, we don't solve this out, I guess, but divide both sides by 180, and you're going to end up getting 5 for an answer to that. And when you have n minus 2 is equal to 5, then you would add 2 to both sides, and you would end up getting 7. And if you remember from the first slide, a 7-sided polygon is called a heptagon. Again, from the heptathlon in track. So we're just plugging in and solving the equation.
Hey, some good news here, guys, is if when you're doing this, you don't get a whole number out, you did something wrong because
Right.
we don't have half shapes.
Right.
Okay, so when you're working through this, if you ended up, all these numbers should be compatible and go into one another. So,
Yeah, you can't
don't
get 3.2 here.
Yeah, so don't get freaked out. I mean, it's got to be a whole number, so that means the division is always going to work out. So don't get scared of these big old degree numbers. Just, do the math real quick, and you should be fine.
Yeah, yeah. Okay. Another example, looking at this pentagon here, we have 4 of the angles given to us. The question is, what is the 5th angle? And so as you look at that, if you knew, you can kind of compare this to the ones that we did with triangles again. If you knew 2 of the angles inside of a triangle, you just subtracted to what all the angles added up to, 180 to get the last angle. So we do the same thing here. We figure out what all the angles inside of a pentagon add up to, which we already did as an example, but we can get that. 5 minus 2, remember, times 180. That would be 3 times 180. And if we do that, we would end up with 540 degrees for a pentagon. That was the example we did 2 slides ago. So in this particular pentagon, they all add up to 540 degrees, and we know 4 of them. So we're just going to take those 4, add all those up, and subtract that from 540. So 110 and 120 makes 230, plus the 85 and 95, all add up to 410 degrees. So if we take those 4 angles, the 410 degrees from 540, gives us 130 left over for that angle A up there. Okay, so the questions could be like that. So we've had 3 different kinds of questions that could show up. You could be asked, what do all the angles add up to in a triangle? They could give you what they all add up to and ask you how many sides it is instead, or they could give you one like this where they're just asking you one of the angles and they give you the other angles inside the shape. All right?
All right, the polygon exterior angles theorem. Now we're going to be looking at if you extend the edges of the polygon out, you get exterior angles. And I mean, this is the really, to me, it's the easier one of the two between the interior and exterior.
Yeah.
I mean, so because the sum of the exterior angles of any convex polygon is 360 degrees. One angle at each vertex, and find x. Now look, so basically, guys, what you need to envision is that you can draw a circle around any of these polygons. And how many degrees is a circle? 360. And so it's bound to that 360 degrees. No matter how many sides, if you have a dodecagon or if you have a quadrilateral, it's still, the outside angles are only going to add up to 360 degrees no matter what. So that makes it pretty easy.
Yeah.
And so when you go to set these problems up, you know, it's the sum of the exterior angles has to equal 360. I mean, so it's really very easy. It's always going to be 360 around the outside. I mean, you have anything.
It's just if there's more sides, like a dodecagon, the angles just get smaller.
Yeah, it's just
That's all.
smaller.
Quadrilateral, if it's a rectangle, they're all going to be 90 degrees. There's 4 of them, and they're going to be 90 degrees. But a dodecagon is going to have 12 of them. They're going to be smaller.
Yeah, so each one is only 30 degrees there.
Yep.
So, so it's real simple, guys. So here it kind of looks like, as Mr. Scritchfield has said to me, it looks kind of like a saw blade. To when you start to extend those sides out, you get the saw blade effect if you have, or if you will. And so basically, all you have to do here is say, okay, I've got a 2x and x plus 30 and 120. Well, I know based on the exterior angle theorem that all those have to add up to 360. So all I have to do is go, 2x plus x plus 30 plus 120 equals 360. There it is right there. Add all these things together. So I got 3x equals 150. Move some things around, and you end up with 210. And then 3x goes into 210 70 times. And
that would be more clear if there was more sides to that, like if that was an octagon. And again, it is critical that you only draw one exterior angle at each vertice. But if we had a picture of one that had more sides like an octagon, it would look like a saw blade.
Yeah.
And so we refer to this as the saw blade theorem.
Right.
It's the exterior angle theorem. They always add up to 360 no matter how many there are. All right?
I mean, it's pretty easy, guys. You just got to get used to doing it.
So, first of all, we need to define back, again, this is something that we should have covered back in Chapter 1 and we didn't do it, but a regular polygon. Okay, you need to know what a regular polygon means. And a regular polygon is a polygon with all sides congruent to each other. So like a regular octagon, all 8 sides measure the same, and all the angles, interior angles, measure the same. So a regular polygon has congruent sides and congruent angles. That's what makes it regular. And again, like a stop sign, that's an example of a regular octagon. So the normal shapes that we think of for each one of these, pentagon and hexagon and octagon and so on, the normal ones are the ones that are regular. When we typically think of them, they are the regular polygons. And so we can look at the different formulas that we had here specifically for a regular polygon. So if it's an individual angle on the outside of a regular polygon, they're all going to measure the same. So like if it was a regular dodecagon, where we were just talking about that if it had 12 angles to it, every angle on the outside, if it was regular, all of them would be congruent to each other. And so as Mr. Videla calculated, if it was 360 degrees divided by the 12 angles that there is, each one of those exterior angles would be 30 degrees. If there was if it was a hexagon, if there were 6 exterior angles, then each one of them would be 60 degrees on a regular hexagon. And so you just take the 360 and divide how many angles there are, because they're all the same, and that's how you figure out what each individual exterior angle would equal. And we can do the same thing with the n minus 2 times 180 formula that was the sum of all the interior angles. If we know it's a regular polygon, we know that every angle on the inside is congruent to each other. They're all the same. And so to find one of those individual angles on the interior, we would take that formula that we had before, the total of all the angles, n minus 2 times 180, and divide by how many angles we have, n. Okay? So these are two very important formulas.
All right, so what we have here, guys, is we have the problem here. We want to find the measure of an interior angle and an exterior angle of a regular nonagon, which would be a 9-sided shape. So what we want to do is to find the interior angle, we want to use the formula of the individual interior angle equals n minus 2 times 180 divided by n. And so n in this case is 9. So when I go to set this up, I'm just going to set it up as, oops, let me change colors here. I'm going to set it up as 9 minus 2 times 180 divided by 9. Okay, and so now 9 minus 2 will be 7, and then 7 times 180, well that's help me out here, Kevin.
Or we could just reduce the 9 and the
Oh,
180
that's true,
because
yeah.
that goes into it 20 times.
So we go like
that'd be
that.
a little bit easier.
There we go. So that would leave me with a 20. Thanks, you. I didn't even see that. So now that makes that really, really easy. So 7 times 20 is 140. Okay? So for the individual interior angle, it's going to be 140. And now for that same exterior angle on the outside, let me just erase this here. Okay, so for that exterior angle now, well now all I do is I use this formula right here, which is 360 divided by the number of sides. So if I do 360 divided by 9, well, 9 goes into 36 4 times, and then I just add that 0, so that exterior angle is 40. Now I want you guys to make a connection here real quick. If the exterior angle was 40 degrees,
which was easier to find.
And the interior angle was 140, what deduction can you make about the way these exterior and interior angles have to make? Or what relationship do those two have with one another? And I'm going to leave you right there with that, and we'll talk about that again in class tomorrow. But look at that. You've got a 40 for an exterior and 140 for an interior. There's some kind of relationship we've talked about in class before, and we'll hit on that a little bit more tomorrow. But I want you to think of maybe coming up with a shortcut for how to do this.
Yeah, and if you looked at it in a diagram, it would make a lot of sense.
Yeah.
So
So anyways,
all right?
okay.
So that's the first section of Chapter 8. We'll see you guys in class.